Actually, this is a project that is, I would say, almost 100% INT project. In a sense, it started here in a previous workshop that I attended. It started due to a talk that I heard during this workshop, this program, and all the participants in the collaboration attended this program. So this is for David that you can write.
Did you get an INT preprint?
Well, no, but I didn't publish anything yet, so I'm okay.
Okay.
So the people that joined forces on this project are Doron Gazit from Jerusalem, Francesco and Lorenzo from Trento, and Bira that is now at CNRS. Okay, it's officially in Paris, in Orsay, but I think he is living in Paris, so you can envy him for that. So this project started when I heard Martin giving his talk about lattice QCD calculations. So I started this talk by telling you what I understood or what I took from this talk, and then we proceed to what I would like to do with these results. So apparently the situation with lattice QCD is very advanced. This is what I discovered. These days, the simulations can go almost to the physical point as long as you consider single baryon or single meson. And what you see here is a plot of the nucleon mass as a function of the pion mass. And all these dots are different simulations, and you see that they go very closely to the physical pion mass. The bands are higher perturbation theory predictions or fits to this data, and they allow you to kind of extrapolate the finite pion mass calculations to the physical point, which is here in blue. So this is for the nucleon mass, and you can see that all the theory is working very, very well. And you can consider also strange baryons, and again, the situation is also very beautiful. This is the nucleon again, this is the lambda, sigma, cascade, they're all reproduced very well, and the QCD calculations go very close to the physical pion mass. So this situation, more or less to date, with respect to the single baryon case. Now we go to the two baryon case or multi-baryon configuration on the lattice. And these are slides taken from this paper of the NP LQCD collaboration, which is the group of Martin here and, well, some other people that will join the department here closely. So what you can see here is the simulation for two baryons. This is in principle a deuteron, this is in principle d neutron, and also some simulations for three baryon systems with different lattice sizes. So what you can read from these graphs is essentially the binding energy of the two baryon system that is given by this gray line. I cannot comment about the quality of the fit or the stability of the calculations. If you have any questions, we have an expert here. What I can say is that with this procedure, one can extract the binding energy of few baryon systems on the lattice. This calculation corresponds to SU3 flavor symmetry. And they were performed with a pion mass of 800 MeV. So this is not the physical point. It's a pion which is much, much, much heavier than the physical pion. Although I've already seen some results with a smaller pion mass, but I will not refer to them at this point. So this is the way the lattice QCD spectrum for few-nucleon system looks like when the pion mass is 800 MeV. So you have a bunch of bound two-body systems. We will concentrate only on these two. This is the deuteron, this is the d neutron. You can see that the binding energy of these systems is about 20 MeV. The d neutron, which is not bound in a physical case, is bound by something like 15 MeV in this case. And the deuteron that is bound by 2 MeV is bound here by 20 MeV. Okay, so here are the difference or the effect of the pion mass on these physical quantities. Then you can go to the triton or to helium-3, which are degenerated in this case. And you see the binding energy is about 50 MeV, actually closer to 60. And also to the alpha particle, where the binding energy is something like 110. So this is the spectrum. So what we would like to do is to take this data and use it as input for nuclear physics. But this will not be nuclear physics in nature, but it will be nuclear physics on the lattice with heavy pions, with pions of 800 MeV. And what we would like to see is whether the technology that we are using to describe nuclear physics in nature also works well for this lattice QCD. And maybe we can use it to study what would be the saturation energy for lattice nucleons with different pion mass. Maybe we will be able to extrapolate it to the physical point. Maybe we can also get more information from the lattice that is probably difficult or impossible in other ways. So this is the grand program that we have in mind when we see this data. Now we see what can be done with it, or at least what we can do with that. Let's be more down to earth. So let's go one step back to nature, to the way people address nuclear physics today. So the point is that, as we see, lattice QCD simulations are still away from the physical point. So they cannot address nuclear physics at the moment. Maybe 10 years from now, lattice QCD will be able to do everything, but at the moment we are still not there. So we cannot derive the NN interaction, the two-body force, from the simulation. So we need another way to bridge this gap between the basic theory QCD and the world that we would like to describe. So the theory that we contemporarily use in nuclear physics is effective field theory. And the point is that this is a phonological approach that you need data to calibrate your information. And in this case, we will replace experimental measurements that were done in real nuclei by computational measurements that were done on the lattice. So what is done in this theory is the quarks and gluon degrees of freedom are replaced by nucleons and pions. And you construct the Lagrangian in a way that is compatible with all the symmetries of QCD. And you make an expansion in low momentum Q, so you have some hierarchy in which you know which terms to include and which order. And all your coefficients that appear in this Lagrangian are, okay, fitted to this experimental data and are in principle functions of some cutoff that you must introduce in the theory, because this is not a fundamental theory but an effective theory. So this is a very famous slide. You probably have seen it dozens of times in dozens of EFT talks, at least those of you who do nuclear physics. Anyway, this is the grand scheme of things in nuclear physics. The theory is a theory of nucleons and pions. There are about 2 free parameters at leading order, 7 at next to leading order, and these numbers grows and grows. but also the fit to the NN scattering improves as you go order by order in this EFT construction. And this is very successful theory in nuclear physics. So now let's go back to lattice nuclei. And the first question you have to address is, what is the appropriate theory for this lattice nuclei? For that, we have to look at energy scales. And there are three important energy scales. One is the mass of the nucleon. The second is the mass of the first excitation of the nucleon. And these two numbers, I will denote them by, this is the mass of the nucleon, this is the delta. Then you have the mass of the lightest meson, which in this case is the pion, which is not that light anymore. And also there is the energy scale that is associated with the momentum scale of this pion. So this is, I will note this energy by E pi. And all these scales had to be compared with the nuclear scale, if you want to be the binding energy per nucleon. So here I make a little table that tries to compare these numbers for three different cases. One is nature, where we know all the numbers perfectly, and then a lattice theory with pions of 400 MeV and pions for 800 MeV, which is the experimental case for this talk. So what you can immediately see is that the fact that you have heavy mesons, heavy pions, means also that the energy scale that is associated with this one pion exchange is very high. Actually, it goes as the mass of the pion square, or almost as the mass of the pion square, because also the mass of the nucleon depends to some extent on the mass of the pion. And if you consider this point, then the ratio between the binding energy, at least if you take the alpha binding energy divided by 4 and compare it to this number, you have an order of magnitude between these two numbers. If you compare it to the natural situation, we have only a factor of 2. Even if we go to pions of 400 MeV, still this difference is quite substantial. So the conclusion from this simple argument is that, in contrast with nuclear physics, where the natural EFT should include nucleons and pions, the natural EFT for this lattice nuclei is a theory of nucleons alone, because the mass scale that involved these massive pions is much, much larger. We shouldn't care about them. So this simplifies things a lot. So the theory, the effective theory for this system then would be very much like pionless EFT in nuclear physics, but with different coefficients. So this is the way you can write the leading order terms in this theory. You have the kinetic energy, then you have 4 contact terms, and then other contact terms with derivatives. And if you do naive power counting, then the orders goes with the derivatives. Actually, things are a bit more complicated. However, we would like to study many nucleon systems. Therefore, we need the potential to be local, and we should avoid a product of 3 spin or isospin operators in the potentials, because this is one of the things that auxiliary field diffusion Monte Carlo, which we are going to use, cannot accommodate, at least at the moment. Fortunately, we don't have any such terms, and if you write the potentials to leading order and add to leading order, this is the way it looks. So we have the leading order 2-body term, we have leading order 3-body term that must be included to avoid Thomas collapse. And then you have also next to leading order 2-body terms. And we define them in terms of the momentum transfer Q and also K, which is the sum of the two momenta. And one should note that non-localities are associated with this momentum K. And if we want to get a local theory, we should in principle get rid of this K. And due to fermionic symmetry, one can actually get rid of all these terms and retain only terms that depends on Q. So after doing this small trick, one get this these three terms for the these two terms for the leading order potential, one for the leading order three body, and a group of terms for the next to leading order, which some of them should be actually zero, depends on the way you construct your potential. The point is that all these terms are local. So yeah.
I keep looking for the three-body term
Yeah.
in your box, and I don't see it. Am I just missing something? You keep saying it includes a three-body
You see, this is 3B, so this means three body. Yeah, but you are right.
But I don't see, oh, you've only got it in the 2B. I'm sorry. It's the left-hand side is 2B, and I shouldn't be looking
Yeah,
for 3B there. Okay.
Yeah, the point is that you should just put
It's
that
always
together
there.
with the three particles. Anyway, at the moment we will consider only the linear order, so everything will be much simpler. We have to consider only these two terms, which means that we have three free parameters. Okay, we have this C1, C2, and this D, which describe the three-body force. Now, a comment about going to coordinate space. So far, everything was kosher, in a sense that we can do everything rigorously. Now, this is the point where we start cheating, in the sense that we leave the path of, how do you say, well, of mathematicians or purists, and start to make approximations. And what we will do, we have to introduce some cutoff in our theory. Okay, as I was saying, these terms, cannot just go there. You have to introduce some cutoff. So the cutoff that we introduce will be in the momentum transfer, and this will lead to a local potential. And this can be easily seen that if we have a potential that depends on these two variables, K and Q, and we make the Fourier transform with this kind of cutoff, then we get this expression for the potential, where R and R prime are the distances of the particle and the incoming and outgoing channel. And the point is that if you have K dependence, you have derivative with respect to this Y. But if you don't have derivative with respect to this Y, then you have this delta Y, which ensures that the potential is local. So anyway, at leading order, there are no derivatives, and doing so, we get very simple expression for the potential. And for the three body, we get something similar, which will be of this form. Okay?
Mathematicians have to regulate quantum field theories. It's okay.
I have a question.
Yes.
Okay. All the identities that you use to, let's say, to rearrange the terms of the potential in order to get rid of the momentum transfer dependence.
Mm-hmm.
These are not real. I think that these are not true anymore if you first regularize and then. I mean, if you put a cutoff.
You are completely right. I was telling that I was cheating. Okay, I was more not cheating, but I'm not rigorous in this respect. That's true. That's true. The order of operations is important. If I would first regularize and then try to arrange the order of the terms, I will not be able to do these things.
So this is because I mean I did this for the three-body force in the chiral effective theory, and then you discover that, for example, a stupid thing is that in pure neutron matter the term tau 1, tau 2 is 0. While if you regularize, it's not 0 anymore. And moreover, I mean, in symmetric nuclear matter, in principle, this term, because of the identity that you mentioned before, in principle, instead of tau 1, then if you fix the coefficient in front of this term on light nuclei, then it is like negative if it is tau 1, 2, and positive if it is central. And then if you apply to infinite matter, this can be, since tau 1, 2 is 1 in neutron matter, this is either repulsive or attractive. So actually fixing this term on, this is not what they're going to do, but fixing this term on light nuclei doesn't tell you anything about this term in pure neutron matter.
Yeah.
So there are, I mean, it's okay, but it is still not clear. So I mean, my idea was, okay, I cannot do this thing anymore, and I have to add more terms in order to account for the...
Aren't these extra terms suppressed by powers of the cutoff?
Yeah, but, yeah, this is true, but in fact they chose a cutoff actually q to the 4th over lambda to the 4th, because they were at n2 and low. So if you expand in that cutoff, you get something which is beyond n2 and low. In this case, for example, if this potential was at n2 and low level, you couldn't use that cutoff, because if you expand it, you would get
That's
q
true.
square over lambda square. You should have used q4 to lambda 4 in order to get something beyond, right? So it's like, yeah, I mean, it can be done, but I still don't understand very well the effect.
Well, we have to look into that.
Yeah.
Some of the problems that we will see later might be related to that. But anyway, this was our ansatz, and we will continue with that.
It was also mine.
What?
It could be equivalent to selectively keeping some higher order terms, right? And
In
some
principle,
which,
yes.
If you have a good expansion, it shouldn't hurt the answer.
I think that at leading order, this should be okay. So at this point, we arrive to the many-body problem. So we can write our Hamiltonian, which has this rather simple form. And we need to solve it. So we have an assorted of few-body methods. For equal to, we use the Numerov. For the light nuclei, we can use spherical expansion. And since we are in a Monte Carlo program, I will mention that for larger nuclei, we would like to use this auxiliary field diffusion Monte Carlo and dedicate 3 slides to discuss this method. So, in order to go to this heavy nuclei, we cannot use a spherical expansion, or definitely not a Numerov method. So we use this quantum Monte Carlo technique, this auxiliary field diffusion Monte Carlo, which is again sampled over many propagators that start with the distribution given by a trial function and propagate in imaginary time. The important aspect of auxiliary field diffusion Monte Carlo is that is the way spin isospin degrees of freedom are treated. And the point, the crucial point is that instead of considering all possible configurations of spin isospin terms, one is doing sampling in the spin isospin space and not only in coordinate space. And this is done, for example, by the following trick, that if you consider this kind of potential that has a sigma term, then the sigma term can be rewritten in this following form using the Abrahamsatonovich transformation in the price of introducing 2 extra integrations. These are the auxiliary fields. The advantage of using this method is the fact that instead of considering 4 to the power of a spin isospin configurations, the number of configurations grows as a cubed. Therefore, whereas the limit of quantum Monte Carlo techniques that use to consider all these configurations is about carbon 12, with this kind of method, you can go up to a equal 90. However, there are some problems that are actually associated with the technicalities of the way people use this method today. I don't know how, to what extent these are fundamental or not. What is clear that the way it is applied today, there is no upper bound property, so it is not variational. And there are problems to include the spin orbit and three-body forces in the propagator. So these are still things that one should consider perturbatively. Was I doing justice? Okay. So now let's go to the experimental data. So our experimental data includes what I've shown you earlier regarding these lattice QCD results. So we have our pions and nucleons, and we have the spectra of the light nucleons. So in essence, we have here 4 data points, and we have 3 parameters. So at least at this level, what we can do is fit these 3 parameters to these 3 data points and predict the 4th one. Actually, we can also predict helium-3, but these come for free. So let's start with the 2-body problem. So here it is convenient to go to the spin-isospin state, and one redefines these parameters in this form. And okay, I have a funny definition of the coefficient. This is not the way people that are grown up in effective field theory will do. So this is the coefficient which is in MEV, and this is the cutoff, and you see that it goes to this line which goes as 1 over lambda to the cube. And then I can use it and calculate the scattering length of these 2 massive nucleons on the lattice. What I do, I just sum these diagrams and get this expression for the scattering length. And what you see, this is the value of the scattering length as a function of the cutoff, because my coefficient depends on the cutoff. So you see that these numbers are fairly stable, and they move between, okay, 1.8 Fermi to 2.3 Fermi, which is substantially large for this system. And what you can see here, there are 2 lines. One is red, which is just simple interpolation of the data, and one is blue, is when I use this formula, okay, or inverse of this formula, to fit the scattering length. And you see that, okay, there is a very nice fit. And if I use this fit, then these are the values that I get for the scattering length of these 2 nucleons on the lattice. And you can compare it to the values that you have in the physical system. So for the physical system, the n pi scattering length in the deuteron channel is 5 Fermi. So this is not that far, I would say. The errors are lattice errors, okay, the errors in extracting the binding energies, and then these are the fit errors, which are much smaller. So this is the first thing that we can extract from this nice exercise. And if lattice simulation can extract this number directly, we can start and make some comparisons.
So
Then
that was done a couple of months ago, actually,
What?
4 or 5 months ago.
Ah,
So
okay.
the comparison can be made.
Okay, I didn't realize that. You didn't publish that yet. Oh,
No, it is published, so yeah.
okay, great. So then we can move to the 3-body case. This is actually a 4-body calculation between these 2 methods, the HH expansion and the Monte Carlo. And you can see 2 things. First of all, that there is a very nice agreement between these 2 methods. That's already reassuring. But you can see also that the binding energy actually goes to -infinity when the cutoff grows. And if you take cutoff of 8 inverse Fermi, then you are an order of magnitude more than the experimental value. And of course, this is due to the fact that we didn't introduce the 3-body force. So we go back to the data, take the helium-3 binding energy, and fit the 3-body parameter. And now we can see how well we are reproducing this number. So for that, we go to the next slide. And here you can see, both in the table and in this graph the binding energy of helium-4 as a function of the cutoff. So in gray, you see the experimental span, okay, the error in extracting these numbers from the lattice simulations. And these two bands to these two lines are the HH calculations and auxiliary field diffusion Monte Carlo calculations, which agree to a reasonable level. The nice aspect of this calculation is that we seem to reproduce the experimental data, okay, at least the lattice measurements, within the published errors. Although it seems that for these cutoffs we are a bit below the value, but okay, this is not terrible. The unpleasant aspect is the fact that we still get dependence on the cutoff, that our numbers are not, I would say, cutoff invariant, which, okay, the theory was perfect, we would expect.
But this is leading order, right?
Yes.
So you should expect to improve this
Yes.
of independence going to next to leading order.
Yeah, this is what you expect. Of course, if we are very close to really low energy theory, you would expect it to be completely invariant, right?
So you'd expect your errors to vary with the power appropriate to having left off the next leading order terms.
So you're not worried about that.
No? Well, I mean, it depends on the power of lambda. I can't see it by eye whether it's the appropriate power. You should do a Lepage plot, where you plot the log of your error versus the log of lambda, and you should find straight lines whose slopes get steeper as you go to higher order.
Okay.
Include every operator. It wasn't clear to me that all the operators at this order were included.
Okay, I will consult both of you later.
Do you have a plot of the three-body interaction versus lambda?
Yes. This is the parameter.
This is the function,
Yeah. This is what you were asking for?
yeah.
Maybe I should have plotted the other way.
What do you mean?
Yeah, divided by, okay, it goes to some constant that when lambda goes to infinity. Okay. Okay. So now we wanted to see if we are able to extract some other quantities from this theory. So the first thing that we wanted to see is the radii of these light systems. And here we found an unpleasant surprise that maybe some of the smart people in effective field theory could help us out. That is that the radius has a strong dependence on the cutoff. So here in blue, green, and red, green, and blue, you see the areas of deuteron, helium-3, and the alpha particles, and you see that they strongly depends on the cutoff. From physical point of view, it is interesting to see that the order is inverted with respect to nature. In nature, the deuteron is larger than helium-3, that is larger than the alpha. Here it is the other way around. But still, the fact that we have such a strong cutoff dependence is definitely not satisfying. But okay, this is still very recent result that we didn't have much time to think about, and I hope to use the expertise in the room to learn how to handle that. The next thing that we would like to do is now go to really large nuclei. Here we can use only the Monte Carlo method, and so far we calculated 1 point in oxygen 16, and what we get is about 50 something MeV per nucleon, which is something like factor 5 with respect to nature. What is interesting is that in nature you would get that the alpha particle is almost completely saturated in the sense that the binding energy per particle doesn't go much beyond the alpha particle. Here we still see substantial growth, a factor of 2. But one have to comment that, first of all, we didn't include the Coulomb force in these calculations, which would definitely reduce the energy, because when you go to larger nuclei, it becomes more and more important. Second thing that we still have to recheck our calculations here. This is very first results. But it's already interesting. So let me summarize what we have done and what we have learned. So I think that these simulations of few-nucleon system on the lattice, this is really a new front in nuclear physics. This, if for many years I was looking at my colleagues in solid state, that they have a new system to explore every 3 years, and we are always more or less considering the same systems. Now we have a new system to play with. We have nucleons with the different masses. But this is not only a game, this is actually a way to better understand our theory, to understand the way nuclear physics goes, and also eventually to extract physical predictions from these many nucleon simulations on the lattice. So I think that it is not very difficult to get persuaded that the natural theory for these heavy pions is just a pionless EFT. So in that respect, it is a very simple theory. What is missing in order to improve on that is, of course, more data. So far, we were limited to 3 data points that were provided by the lattice simulations. But if more data, like, okay, scattering length or other information can be produced independently, then we can go beyond the leading order and see how things are improved and get more robust predictions for the system, and eventually maybe also for larger nuclei. There are some problems in what I've presented, and I hope that we will manage to solve these problems on the way. Yes?
On the radii, when you put a cutoff into a theory, an effective theory, the machinery that you're using actually corrects the Hamiltonian, but every other operator in the quantum theory also has corrections, including the radius operator. And I suspect your problem here is that you're not including the 1 over lambda squared corrections to the radius operator. And so even if you improve the Hamiltonian further, that would probably remain a problem. The problem with it is that it introduces another parameter that you have to fix from your data, and that's the sort of curse of effective field theory. But when you mutilate a theory with a cutoff, which you have to do for this kind of theory, you have no choice, it changes the shape of the wave functions in a way that expectation values of operators are changed. And there is a systematic way of correcting those operators, which you haven't done, I don't think.
No, I didn't.
The radius operator. So it's not corrected to the same order as your Hamiltonian is. And I suspect that you could actually make that much better by putting in a correction. The correction is like a delta function, a sphere delta function, is all it is, times a coupling constant. And the way you tell actually is doing the kind of thing David said, which is to look at the lambda dependence of these errors and sort of see if you're getting the right power law even here.
But do you expect that the radius will present such a strong dependence at this level?
That's what I can't tell from the pictures.
Okay.
But, and the way you do that is you look at what the correction is and ask, how would this correction come in? Could it be this big?
Why wouldn't it be just that? I mean, if I think of the density as just being a delta function operator, why is it not? Why is it more than changing that to the cutoff delta function?
See again? I'm just saying that in the effective field theory, it's just, what he's measuring is the expectation value of R squared to get the radius, right?
Yes.
Right, but if I was calculating the density, and then calculating R squared.
I'm saying the density's wrong.
I understand. I'm just asking why, if I have a delta function operator, why that doesn't just change into the cutoff function.
Yeah, that's what I say a delta function is the cutoff function.
Okay, so could they just smear this with the Gaussian cutoff, the density, with the Gaussian cutoff, and then measure? Is that all that needs to be?
I'm saying take R squared and add the smeared delta function to it, and that combination.
I think it will lead to the
Okay,
same.
okay.
I think it will lead to the same same thing. Yes.
Yeah.
But, but Peter, you're saying there's some unknown coefficients involved,
Yes.
which is
Which I
important.
wouldn't have, that's
Right,
why I
so that's
don't
it.
understand.
I mean, if you looked at insertion of an operator in a Feynman diagram, you'd find divergences, we'd put the cutoff in, but that would require a counter term, and that brings in a new unknown coefficient. So it's not just regulating the diagram, it's renormalizing, it brings in the new coefficient.
And it doesn't seem to give you much, except that it gives you cutoff independence. And if you have more than one radius that you're measuring, you can tune it with one radius and then.
Yeah, but I guess it will put all these graphs together in the sense that if I fix the deuteron, all the others will just be proportional. I will need only one coefficient, all the rest will come.
Probably.
So that would have to come from the lattice calculation
Yeah,
along with everything else.
yeah, probably. But I will probably need only one because you see the problem starts at the deuteron. So, and it actually scales very much together. Yeah, you can scale them, and the graphs are very close. Joe?
So these things are obviously very small because they're heavily bound. It seems to me your main problem is that you're doing leading order calculations. You have no information on P-wave relative interactions or anything like that. Obviously, they're going to come in at those momentum scales.
Yes, in principle you are right. But first of all, we have some hope that.
The alpha particle doesn't really depend on P-wave interactors. There's only 4 nuclei. But once you start getting these bigger systems, it's going to matter.
Yeah, but okay, it depends the way you do it. But the P waves corrections appear higher up, not even in the next.
But they're probably pretty big on the scale of physical things you're considering.
Okay, this we will.
But you need some lattice information on.
Yes, yeah,
Depends
exactly.
significantly on P-wave interaction,
Yes.
which you don't.
Okay, maybe if there are calculations of helium 5, or lithium 5 on the lattice, we already get this kind of information. At least we see what we're missing, what's going on there,
Or
right?
one state of 2 neutrons or something like that.
Or
Yeah.
yes,
So this kind of data can immediately be incorporated if we see that.
I guess related to Joe's comment is that when you have a large nucleus, what's the small expansion parameter? You say, well, it's a momentum over a length scale, but why would the momentum be small?
Yeah, that's the question of what is the Fermi momentum in this nucleus and how it is related to our expansion parameter. So this goes back to the energy scales that I discussed, and that's true that I should have, where is it? Somewhere here.
Yeah.
Should be another energy scale, which is the Fermi momentum or the Fermi energy for larger systems. Naively, I took this number, but which is okay, of course, wrong. But still, it seems that if you consider these scales, there is a way to go before it saturates. So I think that in this case we are rather safe. That not like a pionless theory in nuclear physics, in natural case, that you immediately run out of the bounds of the theory. I think that here you are on the safe side, but of course we have to check that. But already in this oxygen 16, the number of energy per nucleon was 50 MeV, so I think that's not bad.
In the cutoff, why can you take the cutoff much larger than the lattice showed earlier, like it goes all the way up to 8.
Yeah, in principle, these are two unrelated issues. One is to check the renormalizability of the renormalization group properties of the theory, right? Just to see that you don't have funny things in the theory that when the cutoff runs away, all the predictions run with it. Okay, this is just kind of, if you want, a mathematical aspect that the theory is okay.
Consistent with the physics, essentially. It's kind of still mathematical, it's important. Mathematical, I mean, from the point of view of the numerology, it's important to see whether the quantities are.
Yeah, I think it's a dumb question, but why isn't just enforcing flatness in lambda a strong enough condition to determine the coefficient on the Gaussian?
You mean to get kind of a local lambda invariant and not overall? Well, first of all, it is not clear that you get it anyway. So, for instance, if you look at this alpha plot, where is it? There is no place that it is really invariant, right? Or it doesn't seem to be the case.
I mean, you have to add this term, which requires the coefficient you don't know. The claim was you need to do a lattice QCD calculation to figure out what that coefficient is. But I'm saying, can't you determine the coefficient by self-consistently forcing the...
Usually you can force it to be flat for one thing, but it won't be flat for something else. And what you're doing is you're changing the sort of degree to which it's flat for everything. And so a criterion like that you could apply to one parameter to fit a parameter in one context, but if that parameter enters in some other context, it will probably have lambda dependence, because you need higher order terms with more couplings in order to remove all the lambda dependence.
Okay. I just thought that in this case there was, the assertion was that there's only one term missing in some sense.
There's always another term. That's the question. I can't tell from this picture whether this is consistent with coming from the next order term, which again is what David asked
Okay,
early on.
this will need to analyze.
The errors on a log-log plot, look for the slope, but it's hard actually.
So from the last point of view, it seems to me that reducing the uncertainties in these calculations would be useful.
Yeah. Yeah.
So do you have an idea of how much, what sort of reduction would impact things? At least for this order.
We didn't analyze it yet, but at least my feeling is that if we will put, the errors that comes from the coefficient, in a real sense, trying to vary the coefficients to the bounds of your error, then we will get really substantial effect.
We tried a little bit to play with this in the Monte Carlo, and we didn't show the plots because this was from some calculations that have some problems there. But I mean, from the qualitative point of view, essentially, if you take your coefficients in such a way that you are compatible, say, with the fit of the three-body system, the energy of the three-body system, you don't go very far. I mean, you still have many possible curves depending on the cutoff, but the energies do not go very far away from that band for the four-body system. So apparently there is some freedom that is due to the fact that the uncertainty, is large in the QCD calculations, but there is no inconsistency, let's say, or no strong inconsistencies. You never get binding energies of 50 or 200, let's say.
Right.
So more or less, this is tells me at least that overall, I mean, we are in the right ballpark.
So if the lattice calculations could reduce this uncertainty by, say, a factor of 10, then you'd start seeing where things were.
Oh, exactly.
So that would be very constraining for these calculations.
In that case, yes. That would be.
So 10 is kind of a dream, but is a factor of 2 or 3 useful?
I think so, yes.
Oh, yes. Yes,
okay, so any
absolutely.
reduction in the
A factor
uncertainty,
2 would already probably
Yeah.
constrain things in
Okay.
a much more useful way, because at that point probably you can start to see,
Yeah.
if there are discrepancies, then you see them, and then you can understand, I mean, if it is a matter of really adding contributions to higher orders, or somehow whether, I mean, because my feeling is also that here, if you pick up some parameters in such a way that you still are within your boundaries, you can artificially reduce the dependence a little bit. I mean, depending on the balance of the 2 and 3 body force.
Yeah, but I think that we need to answer this question, we need to do some more systematic
I mean,
work.
Some fake data analysis.
Yeah.
Exactly.
Okay.
Okay, so let's thank the speaker.
Oh, I'm asked if we can postpone a little bit the discussion this afternoon, so instead of